Remember how simple life was thanks to your favorite products?
Fabulous.
And how things were just better thanks to new and improved ways to do basically everything?
Oh, there's no question about it. Ted has a softer diaper.
But if it seems too good to be true, you might wonder how we got here. Thank the chemists. For a lot of these products, we can thank the development of PFAS. You may not know PFAS, but PFAS knows you, and it's everywhere, including inside you. This is important because we now know that PFAS can create health problems like cancer. PFAS is short for per- and polyfluoroalkyl substances. They're called forever chemicals, and they've been developed over decades. They go into things like non-stick Teflon pans, fabrics, furniture, and even makeup. Another big problem is PFAS is in our drinking water. So how do we get rid of them? We've been purifying water for millennia, and it was only up until 1804 when the first municipal water treatment plant was built in Scotland. There they used sand. Some operations still use sand, but there are other methods as well. But the problem with PFAS is that they are created with some of the strongest bonds in chemistry, so they don't break down. Over the years, PFAS has seeped into the ecosystem, our food supply, and our water supply. And cities and towns are always on the lookout for solutions.
This is like the world's largest Brita filter.
Brita filters, like you may see in your kitchen, use granular activated carbon, or GAC, and it's a common way used by commercial operations to reduce PFAS levels today. In fact, the Sweeney Water Treatment Plant in Wilmington installed 8 giant GAC beds in 2022.
What happens is, as the water flows over the granular activated carbon, PFAS sticks to the surface. It has a lot of surface area. And that's why one of the reasons it's very good at removing PFAS.
Data from recent studies by several government agencies show that GAC removes PFAS from water, but the findings from the studies differ on how much PFAS is taken out.
We developed at UNC.
Since there are a number of ways to purify water, Sweeney recently invited Professor Frank Leibfart to test yet another method inside their plant.
The real change in philosophy we took is all resins previously were developed to take all the junk out of water that is typically in water, right? There's organic matter, there's ions, this is all stuff you don't want to drink. And those were kind of, catch-all solutions that would be thrown at every new contaminant. But PFAS is different because PFAS is dangerous at incredibly small amounts.
The Environmental Protection Agency started investigating PFAS as far back as 1998. And up until then, there had been a patchwork of regulations that emerged as more scientists discovered what was going on. But by 2024, the EPA set its first ever limits on PFAS in drinking water to their lowest levels in history.
This is a drop of water in 5 Olympic-sized swimming pools.
In 2017, Leibfart was at a faculty meeting and was asked if he knew a way to get rid of them all. He was a new father then and knew that something called a hydrogel made diapers work.
A hydrogel takes water, right, out of materials, and I actually just had a son recently, so we were using a lot of diapers, right, and diapers are amazingly efficient at absorbing water, so I said, what if a fluorogel could absorb florist material in the same way? And we really wanted to get it right before we started running it.
Who knew diapers could inspire technology to get rid of PFAS? PFAS are what are called fluorinated molecules, which is when a fluorine atom is bonded with a carbon atom. Again, very strong and hard to get rid of. Leibfart and his team have come up with what they think is a promising solution. It's called ion exchange. The process is where these impurities are exchanged with ions of safer chemicals, usually sodium or potassium. One of the big differences in their process is that their resins can be cleaned and used again, where normally a lot of GAC is landfilled after one use.
So what do you tell me what you're doing, Emily? Ion exchange resins have a greater capacity for PFAS removal compared to granular activated carbon, meaning that they can remove more mass of PFAS per mass of sorbent compared to granular activated carbon.
But just because it works in the lab, it means very little if you can't make it big enough to handle the water of a treatment plant like Sweeney. And that's what they're doing here in their lab in Morrisville.
Field development, so we're basically working out the formulation and just seeing which ones are the most effective. And then we scale it up, so then we figure out what the ideal reaction conditions are, and we optimize those conditions.
Each of these columns contains a different material.
So back to the pilot. Water coming into Sweeney is siphoned off through these tubes. 2 tubes hold versions of their resin, and the others have water samples cleaned by traditional methods currently used at Sweeney and other water treatment plants. Leibfar says to get the best data possible, the pilot will run for about a year. He says they got to this point by thinking outside the box and is excited about the results so far, but adds no solution will ever be perfect since there's always more to discover.
Thanks for watching. If you enjoy science stories like this, like and subscribe for more.